Today, in this video, we will see derivation of shearing stresses in the beam. This beam, breadth small b and depth small d, consider one elemental strip at a distance y from neutral axis. This is shear stress distribution diagram. This triangular portion on AB and CD of this beam is shear stress distribution diagram. And from neutral axis up to outer fiber, this shear stress distribution is shown. And this m at AB and m plus dm at CD are bending moment. There is sliding of layer within this section because of this bending moment. Because of this m and m plus dm, there is sliding of layer within this section. And because of sliding of layer due to tangential forces, there is shear stresses which is induced inside the beam. See, because of this bending moment, there is sliding of layer within the section, and because of sliding of layer due to tangential forces, there is shear stress induced inside the beam. We will see this derivation step by step. First, consider let this EM is bending moment at AB. M plus dm is bending moment at CD. F is shear force at AB. And F plus df is shear force at CD. Consider an elemental strip EF at a distance y from the neutral axis as shown in figure. This elemental strip EF at a distance y from neutral axis as shown in the figure. Right? Consider again, sigma is bending stress on this sigma is bending stress across AB at a distance y from neutral axis. And sigma plus del sigma is bending stress at CD at a distance y from neutral axis. And I is moment of inertia. So right here, sigma is bending stress across AB at a distance y from neutral axis. And sigma plus del sigma is equal to bending stress across CD at a distance y from neutral axis. and I is moment of inertia about neutral axis. Now by using flexurer formula, m by I is equal to sigma by y. From this formula, sigma is equal to m by y into I, and this sigma stress on face AB, and for face CD, sigma plus del sigma is equal to m plus del m upon y upon m plus y. Here see this y, this side, m into y upon I, and similarly m into y upon I. This is on face CD. Now FAB, force acting on AB. Force is equal to stress into area. So FAB is equal to stress into area. FAB is equal to sigma into delta A. And sigma is m into y upon I. So FAB is equal to sigma is m into y upon I into del A. Similarly, for FCD, FCD is equal to m plus del m into y upon I into del A. So DF is equal to net unbalanced force. Therefore, DF is equal to this force on CD minus force on AB. Greater force minus smaller force. Force on CD is greater. Force on AB is smaller. So force on CD minus force on AB. Therefore, del F is equal to force on CD is this m plus del m upon I into y into dA. minus force on AB is M into Y upon I into dA. Take common this Y I and this dA. That means Y upon I into dA take common. The remaining term M plus dM minus M. This M get cancelled. Net unbalanced force is equal to dm upon I into y into a. This dm, take here, dm upon I, this I, into y into dA. This net unbalanced force which is required for the sliding of the layer within the section. Now capital F is equal to total unbalanced force. So for total unbalanced force, integrate this df, integration of df and integration of this dm upon I into y into dA. Integration of df is equal to integration of dm upon I into y into dA, and y here y is equal to 0 and y is equal to d by 2, boundary conditions. Therefore f is equal to dm upon I, integration of y is equal to 0 and y is equal to d by 2 y into dA. F is equal to dm upon I, integration of y is equal to 0, boundary conditions are from 0 to d by 2 and y into dA. This y into dA, integration of y is equal to 0 d by 2 y into dA is first moment of area under consideration from neutral axis. That means this is a into y bar. This term is a into y bar. A is area and y bar is neutral axis. Unit of this term is mm cube. Now shear stress which is induced because of the sliding of the layers. See this figure. Because of sliding of this layer, there is shear stress induced. Shear stress which is induced because of the sliding of layer will be equal to sigma is tau is equal to force upon area. Shear stress tau is equal to force upon area. Tau is equal to F upon area is B into dx. This force is nothing but the dm upon I into ay bar. Upon b into dx. And from this equation, tau is equal to dm upon dx ay bar upon y, ay bar upon I into b. That means ay bar upon this b into I. And this dm upon df is the rate of change of moment with respect to distances. That is nothing but the shear force. Right here, dm upon dx, the rate of movement with respect to x, rate of change of moment with respect to distance x. That is nothing but the shear force. Therefore, tau is equal to shear force is denoted as S ay bar upon bi. This tau is shear stress and S is shear force. Tau is shear stress and S is shear force. So see, derivation of shearing stress in the beam. Consider one elemental strip at a distance y from neutral axis, and these triangular portions are is nothing but the this triangular portion is shear stress distribution diagram. On face AB, this M moments act. On face CD, this M plus DM moments act. And this W is uniformly distributed load on that beam. And this EF is small elemental strip. M is bending moment at AB, M plus DM is bending moment at CD. F is shear force on AB, F plus DF is shear force at CD. I is moment of inertia about neutral axis. Sigma is bending stress across AB at a distance y from neutral axis, and sigma plus del sigma is bending stress across CD at a distance y from neutral axis. Now consider elemental strip EF at a distance y from the neutral axis as shown in this figure. For solving this derivation, use flexure formula m by I is equal to sigma by y. From this flexure formula, we get sigma is equal to m by I into y, and this sigma is on face AB. The stress is on face AB, and now for calculation of stress on face CD, this sigma plus del sigma is equal to m plus del m upon I into y. Now FAB is force acting on AB. For calculation of force acting on AB, force is nothing but the stress into area. Stress is denoted by sigma. Area is that small elemental strip area del A. F is equal to F AB is equal to sigma is m into y upon I, and this del A. And for face CD, force is similarly stress into area. Stress is m plus dm upon I into y into dA. dF is net unbalanced force. dF is equal to bigger force minus smaller force. Bigger force is force on CD and smaller force is force on AB. So put this values force on CD here and this force on AB value in this equation. We get net unbalanced force is dm upon I into y into dA, and net unbalanced force which is required for the sliding of net unbalanced force which is required for the sliding of the layer within the sections. So F, now calculate F is equal to total unbalanced force. Integrate this del F term and boundary condition 0 to d by 2. That means at center neutral axis, this 0 to d by 2. And from this we get this total unbalanced force is equal to dm upon I into a into y bar. And from tau shear stress equation, force upon area, F is equal to area is this B into dx, we get shear stress is equal to shear force into A into y bar upon B into I. And this del m by del x is nothing but the rate of change of moment with respect to distance x, that is nothing but the shear force. This is shear stress is equal to shear force into A into y bar upon B into I. So this is derivation for shearing stresses in the beams. Thank you very much.